So something I sort of ended in one lecture and didn't continue in the next lecture. So this example 1.3.3. So I started this off, but somehow the video got cut off for some reason. Let me finish this exercise. So what are the example? The example was a pair of dice are thrown, right? And you're also given the following, that one of them shows a 4. If one of them shows a 4, then the question was, what is the probability the other die shows a 6? That was the question. So let me try and answer this. I'll try and solve the example now. It's in my textbook as well, but let me just sort of so in some sense, this problem, the way it's defined is you're given some information of some event occurring, and based on that, you want to find the probability of another event. So this falls under what we defined so far as conditional probability. And conditional probability means you have one event. Let's call that event as B. So one event is, let me erase this. Sorry, one event is B. B is the event. One of the dice shows a 4. Right? That's the event B. So I'm rolling 2 dice. So when I'm rolling 2 dice, then one of them is showing a 4. So let's try and write down all outcomes where the first one shows a 4. So it's 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, and 4, 6. So that covers all possibilities where the first die shows a 4. Then I have the second die as well. So that's going to be 1, 4, 2, 4, 3, 4, 4, 4 I've already counted, so I'll forget about it. And I have 5, 4, and 5, 6. So this is all the outcomes in this experiment, which consists of the following, where one of the die shows a 4. What's the event we're interested in now? The other die shows a 6. So let's write the following. Let A be the event, one of the dice shows 6. So how do I do this now? This I have to just check the spreadsheet if anything. Anybody has said anything? Okay, nobody has said anything. Okay, very good. So someone has comment on the website. I will try and look at it at some point. So here, what happens is that this is going to be equal to, one I show the 6 is going to be 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. That's 1. And the other one is going to be, again, the other one shows a 6. So 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. And I've already understood 6, 6, so I will not count it again. Very nice. So these are 2 outcomes that we have. And what are we interested in? We know that one of them shows a 4, that means B happens, and we want to show the other shows a 6. So we want to find the probability that of A happening given that B happens. So the question is, so what's the question is, what is the probability of A given that B has happened? Okay, this is what the question. So this is, let me write this down in green. So the English way of thinking about this is probability that A happens given that B has already occurred. This is what you have to find out. Very good. So now this, by definition of conditional probability, this is going to be equal to probability of A and B divided by probability of B, provided probability of B is positive. So we have to check this. Once we check this, then we can just this derivation is done in the video as well, and in section 1.3 in the book. This material is covered in section 1.3. So we make a note of this. This material is covered in section 1.3 of the text and the videos and the course video. How this formula came about and why this is so in some sense it's kind of restricting your sample space to B and looking how A occurs inside B. That's how this comes about. But we'll write this down. So now let's just check if probability of B is positive. So how does one check that? So now you're rolling a die. The experiment S is, sorry, S is, I want you to color again. S is the total sample space of all outcomes of rolls of two dice, right? Of rolls of die 2 times or 2 dice. I'm not sure what I said. Let me just check my question again. A pair or a pair of them. So now what is it? Now immediately you know that by this I immediately know that the first one can be a 1, second one can be a 1. I can keep going all the way till the first one can be a 1, second one can be a 6, and so on and so forth. I keep going. I start at 2 again, and 2, 1, and so on and so forth. I can enumerate all the outcomes, and I reach 6, 6. And there are 6 possibilities for the first one, 6 for the second one. So size of S is going to be equal to 36. And like we discussed in the previous section, we know that this is part of what's called an equally likely outcome experiment. So in an equally likely experiment, we know that the probability of B is going to be equal to the size of B divided by 36. But that's just how equally likely outcome experiments are defined. So now if you go above, you look at the size of B. What size of B? It has 1, 2, 3, 4, 5, 6 in the first row, 1, 2, 3, 4, 5 in the second row. So there are 11 elements in the size of B. In B, size of B is 11. So this is equal to 11 by 36. And it's indeed positive. So therefore, this formula will hold true. That is, probability of A given B is going to be given by probability of A and B divided by probability of B. We make that in blue color, so it's consistent with what we're trying to do. Very nice. So we make this also in blue, so that's nice. Very good. So that's easy to solve. So now, what is the conditional probability? It's of A given B. It's probability of A and B divided by probability of B. But what is A and B? A and B means elements that are there in A and are there in B. So let's look at that. So what are elements in A and B? So we can, if you do a simple sort of a check, if we look at 4, 6, that should be there in A and B as well, because 4 is in the first row and 6 in the second one. That's definitely here somewhere. It's here. We should also have 6, 4. We should also have. I think I made a mistake here. Right? It's 5, 4, and this is 6, 4. I'm sorry about that. The 6, 4. I made a mistake here. So this is 6, 4. So this is also an element that's there in A and that's there in B also. Exactly. So A and B have 2 elements in common: 4, 6, and 6, 4. Let me undo these changes so the notes are clear. Oh, sorry. Let me make this as erase this and 6, 4. So I come here. So now I know, first thing I know is A and B we discovered was the set 4, 6 and 6, 4. Therefore, probability of A and B is the same as the size of A and B divided by the size of S. The size of A and B is just 2, and size of S is 36. So it's 2 by 36. Very nice. So therefore, probability of A given B is going to be equal to probability of A and B divided by probability, which is equal to A and B was 2 over 36 from the top. Probability of B was 11 over 36 is equal to 2 by 11. That's what the problem asks. So that's the answer. So there's one observation I'd like to make. It's just a simple observation, just to sort of illustrate the fact that of conditional probability. So here, you notice, what is the probability of A? The probability of A is the size of A by 36, size of S. And what's the size of A? The size of A is going to be right here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, that's 11. Size of A is 11. It's 11 by 36. So notice the occurrence of B does affect the probability of A, right? So the occurrence of B does affect the probability of A. Therefore, as seen, so therefore A and B are dependent events. A and B are dependent. They are independent events. They're dependent events. As the probability of A given B is not equal to the probability. So this was 11 by 36. This is 2 by 11. Very nice. Very good. So this is one thing that I wanted to sort of clean up. So let me show you the double view so that you sort of keep the whole problem in one, get to see the whole picture in one slide. Let me go and check it. Yeah. Right here. Very nice. Make it a little bigger. Very cool. So the one thing that I had missed out on the videos, I'm sorry about that, but I hope this clarifies that. Let me look at the sheet, Google spreadsheet, see how it's here. Okay, so the website, they can't find the link. So just go to my homepage, click on teaching, and there will be a link to NPTEL. And in that page, all this is there. I think you have typed S, it should be a tilde. And teaching is capital T, I think, and NPTEL is all capital. So those things matter on the UI. One person has said it, so I'm sure. Very nice. Good. This is one example I wanted. Okay, let me go to the next example. I'll let you sort of let this sink in for a couple of seconds, or maybe 30 seconds. Let's get the other example. If the example was not clear, just send a thing on the chat. I will monitor again, explain anyone. Okay. Very nice. So let me try and sort of do a little bit more conditional probability. If there are no more questions on this problem, since I've not seen anything on the chat, I'll just carry on. Okay, let me write down a question that is not there in the homework in assignment. So I'll try and see. finish. So let me call this as next one as is my problem that I want to do. So let me just draw a different color, perhaps pink. So let me call this as exercise. Let me call this live exercise 1. So you have a number for it. So here I'd like to sort of pose a question that we can think about and solve. And they're very interested in, they're sort of along the lines of conditional probability. And some of you had sort of spotted that, okay, I'm giving questions on picking things in order, not order in the assignment, and are not covered in the program. And such things I assume that you might know in the course before you come into the course as a prerequisite, so, which I didn't have to sort of do in the class. But here's a problem that I will do, which I think you might benefit from the same sort of idea. So let's say a box has m balls, and let's say all of them are red. Okay? Are red. So there are m balls in a bag, in a box. All of them are red. Okay? So maybe I should write it as instead of saying are red, I'll just say of which are red. And of which are. Right. Now what I do is I go and sample n balls. So we sample n balls. We sample n balls. So little n balls. Let me write it in blue. Little n balls from the box. Okay. With, of course, if you can't sample more than r, so let's say with n less than or equal to r. So I don't want to clean out the red balls. I want less than or equal to r. And of course, I also want to do n is less than m minus r as well. So it's like a sort of in the middle of I don't clean out the red balls and not the red n balls. And we sample them in a way without replacement. Okay, so sample n balls from the box without replacement. So once I pick a ball, I don't put the ball back. So I pick a ball first in an equal likely manner. I leave the ball outside. I go pick another ball, and so on and so forth. I draw little n balls. So now let Aj, this is experiment. This is the box, the experiment. Let A sub j equal to 1, J sub j be the event that the ball drawn on the jth draw is red. So ball drawn, maybe I'll call this R sub j. So R sub j, R sub j be the event that the jth ball drawn is red. Sorry about that. Thank you. I apologize for my handwriting. Sometimes it's kind of unreadable. I'll try and fix it as I can. But, you can post in the chat if something is not clear. So, is that clear? So the probability Rj is the event the jth ball drawn is red, and I want to understand. So let's say j is equal to 1, 2, and 3. Let's say I'm looking at that right now. And let's say n is larger than 3, and so is capital R and so on. So let's see what's probability of R1. What's probability of R2? And what's probability of R3? So that's the questions. So that's the exercise. So I'll let you think a little bit how to solve this problem, and I will solve it in about 2 minutes time. Very nice. So let's see. I'll give another minute to think about how to solve this problem. Okay. So now, what is probability of R1? Let's do problem. Let me change the color. Question to be maybe same as color as the purple one. Let's see if I can get the purple across. Let's go here. Let's. So what's the answer? It's the answer. Very good. So what's the answer? So what is probability R1? R1 means I'm going up picking a red ball. I want to pick a red ball. So, and I have total of m balls in the bag. So probability of R1 will just be total number of red balls divided by total number of balls in the bag. So it's just R by M. So it's R by M. R divided by red, so it's color red. Let's do that. Yes. So probability R1 is fairly clear. You have m balls in the bag. You're picking one ball out. You have R good possibilities. It's an equilateral experiment. Nice. Now, what is probability of R2? R2 is a little tricky. So in probability of R2, it's a little tricky. So how do you do this now? You have to worry what happens in the first draw because you're doing without replacement. Right? So probability of R2 is probability of R2. And in the first round, R1 happened. Or the other possibility is R2 happened and R1 didn't happen in the first round. That's how maybe I had too many colors, so we put just a black here. So in the first, you understand what happened in the first draw. First draw red could have been chosen. In second, first draw red may not have been chosen. Now there are two mutually exclusive events. This is mutually exclusive. This event happens and this event cannot happen. They are mutually exclusive. So you can use the laws of probability. So to get, what do you get? You get probability of R2 and R1 plus the probability of R2 and R1 complement. This is what I think. Very nice. Now again, I just do a little jugglery. I know this is going to be the same as, because I only know the condition probability. Because every time I pick a ball, I know how many balls are there in the bag and what sort of balls there are there. So what I can do is I can write this as probability of R2 given R1. Sorry, R2. Let me write this in red. R2. So I'm interested in given R1. I'll leave this in plus probability of R2 given R1 complement. And I multiply it by probability. This moves across. This times probability of R1. This times probability of R1 complement. This just follows from conditional probabilities, right? Because this is okay because probability of R1 and probability of R1 complement are both positive. Right? That is from here, because from this I immediately know probability of R1 complement is just going to be m minus r divided by. So it's also positive. Very nice. So once I'm here, I finish the problem. I go here. I get this R1. I know is just going to be r by m. This is r by m. This is m minus r by m. So it's m minus r by m is R1 complement. Probability of r is R1 is r by m. These two people, what do I do now? I'm trying to calculate probability R2 given R1. That means in the first draw, I've already chosen a red ball. So one red ball is already gone. And there are only m minus 1 balls left, there are only r minus 1 balls left of red. This one is going to be r minus 1 divided by m minus 1. This one, in the first draw, I have not picked a red. So all the red balls are there, but the number of balls have become m minus 1. So the bottom is m minus 1. The top one remains as r. Very nice. So now I have to do the algebra here. So this becomes m and m minus 1 is common in both the parts. So I can write in one denominator. So I have m into m minus 1. In the top, what happens? In the first term, I have r. I have r here as well. So let me write this down. R minus 1 into r plus r into m minus r. This is what I have, right? So I keep going down. I have r common. So I remove the r outside. And I have inside, what do I have? I have r minus 1 here. And here I have m minus 1. And I have plus m minus 1. M minus 1. So write the whole thing in black. So it's easy. So I write this down. R minus 1 plus m minus r. And the whole thing divided by m into m minus 1. If I keep going down, so I get top is r. So I need to keep my convention correctly. Oh, God. The top is r. And then inside I have m minus r plus r minus 1. The r cancels off. So I cancel the r off. And I get m minus 1. I get m minus 1. The whole thing divided by m into m minus 1. The m minus 1 cancels. So I'm again left with r by m. So kind of nice, right? So I've shown you that probability of R2 is also equal to m by r by m. Very nice. It's kind of a nice idea. I like it. That is, even though you're doing with replacement, without replacement, your probability of choosing a red ball remains the same as you keep going on. It's a nice observation. So let's do the next one. Probability R3. So how do we do probability of R3? Let's see how much space is there. Let's do the next page. What is probability of R3 now? Let's see. Probability of R3 is going to be what now? So I'm already a third draw. That means I have already done the first two draws. So I already picked. So let's say R3 is the event that the third ball drawn is red. Right? Third draw results in a red ball. That's what R3 means. That means anything can happen in the first two draws. You could have a red or not red ball, first two draws. But the third ball has to be a red. The third draw has to be red. That's what this picture is. So it means I have to sort of use this event. I have to sort of exhaust all that happens in the first two draws to compute the probability of R3. So what do I do? So I do exactly that. Right? So I do probability of R3. And I have to exhaust all possibilities. There are four possibilities, right? I could do red, red, black, and so on. Let's do that. So what happens is I could have picked red in the second one and the first one. So I'd have R into R1, R2, and R1. That is all three balls were drawn red. Or I could have, let me write down in this time in the color coordinated way. Or I could have had R, let me go by red. The third always going to be red. So it's oh God. So the second one is R3, and I could have had let's see, and R2 complement. In the second one, I didn't pick a red ball, and the first one I did pick a red ball. That could be one more possibility. Or I could do the next one. Sorry, let me do the next one. Is I could go and pick R3, and let's say I didn't pick a red ball in the second one, and I didn't pick a red ball in the first one. That could be third possibility. And the last one left is let me write it down in red. And the last one left is maybe I should just is equal to union. One more possibility is there. And what did I miss? I missed the fact that you could pick a red in the third one, which you have to pick. And you could have picked a red in the second one, but not a red in the first one. That's the fourth possibility. So all these 4 possibilities will add up to the probability of picking a red ball in the first and third draw. Because you've exhausted what all happens in the first 2 draws. Red, red, no red, red, no red, no red, and red, no red. Now they're all mutually exclusive. They're all, so you can add them up. So it's going to be, and now I'll add in only one color. So it's sort of a probability of R3 and R2 and R1 plus the probability of we have R3 and R2 complement and R1 plus the probability of R3 and R2 complement and R1 complement plus the probability of R3 and R2 and R1 complement. So it's R2 complement here, this R2 complement and R1 complement and R1 complement. Whereas these are 4 possibilities. Now you must know how to handle each of the probabilities. So now this is where we have done a thing in the book. Let me just look at the book. This is theorem. When you are finding intersection of many a string of intersections, this is called the law of. It's the name for it. I forget. The name's drawing a blank right now. But this is theorem 1.3.8 in the book, where you can successively condition. So it's theorem 1.3.8 in the book. You can use that. And what do you do with that? You can get. Sorry, let me just raise this. Let me just move it a little bit. What you could do is you have R3 and R2 and R1. You can successively condition because you know how to print the conditional probabilities because you're drawing without replacement. So your probability of this R3 given R2 and R1 times the probability of R2 given R1 times the probability of R1. That's what the first term looks like. Plus, second term will look like the same thing. Let me just get this back on track. 1 second, sorry. There's. Right. So second one looks like what? Probability of R3 and exactly what you have, right? You have this R3 and probability of R3 given R2 complement and R1, then probability of R2 complement given R1 times probability of R1. We'll have that here. And you have plus probability of R3 given R2 complement and R1 complement, and then this will come and write it in a second. This will be probability of R3 given R2 and R1 complement plus probability of times probability of R2 given R1 complement. That's all. Let me get it down. So this is R2 complement. This is R2 complement here. This will be R2 complement and R1 complement. This probability of R2 complement given R1 complement and probability of R1 complement. This is R2 complement, R2 and R1 complement, R2 and R1 complement, and probability of R1 complement. Very nice. That's what you will get. But now you know how to compute each of these probabilities, right? Because each of these are well defined. This is R by M. This again, you know, it's R minus 1, R minus 1 by M minus 1. This is R minus 2 by M minus. So let's write that down. So it's going to be equal to, the first one is going to be R minus 2 by M minus 2 into R minus 1 by M minus 1 into R by M. That's what the first one is. The second one, what happens, you'll be a little careful. You pick the first one as R1, so that remains as R by M. That's no problem. The second one, you have to be careful because you pick the first one and you don't want to pick a red ball. So you still have M minus R of them left. So it's M minus R by M minus 1. That's what the thing is. This is probably orthogonal. The next one is going to be what now? You have to pick R3. You have picked not a red in the first one, second one, and then the last one. So you only have R minus 1 left. So you have R minus 1 divided by your M minus 2. Right, that's the last one. Then the third one, let's say third one here is going to be equal to what now? probability of R3 and R2 complement. Maybe write it below, so it's logically clear. Third one is going to be plus. Here I have the first one, I come with the reverse order. So I have m minus r by m. That's the first one. It's no red. Second one, again, I don't pick a red, and I know I don't pick a red in the first draw as well. So I have m minus r minus 1 to choose from, and I have m minus 1. On the last one, I have to pick a red because the third ball is red. So I have all of them left, and I divide by m minus 2. And what's the last one? The last is R3, and this is the whole thing. So let's write down. This first one again is m minus r by m. The second one, I am picking a red, given I picked no red in the first one, so I have r left, and I have m minus 1 left at the bottom. And the last one, again, I have to pick a red, so I have r minus 1 left, and I have an m minus 2. Very nice. Now, if you do the algebra, since I'm running short of time, I have 4 minutes left, I do the whole algebra, you will get the bottom is always going to be m into m minus 2 into m minus 1 into m. That's the thing. And the top, you have to add all the terms. You have r common everywhere, so you can remove the r. And you have r minus, and everything else you have to add up. You get a bunch of terms at the top. If you do the algebra, I'll leave as an exercise to do the algebra. What will happen is, amazingly, you will still get r by m. So even the third draw, you will end up getting r by m. It's a very nice sort of a problem. So let me try and recap it for you, so you sort of see it together. Let me get this down. A bit smaller. Start off here, so let's go here, and then let's come down here. Very nice. Quite cool. So the idea is that you will always pick a red ball with r by m. So even though you're doing without replacement in this problem, you'll always, it doesn't affect the chance that how the red ball is chosen. It's sort of an intricate part of the experiment. That is, even without replacement, the chance of picking a red ball is always going to remain as r by m. So here's a sort of an, I'll give an exercise for you to sort of think about. So here's a sort of an, I'll leave it to question to think about. So I will not solve today, to think about it. So question to think about. In general, what is probability of Rj for any j? So we have shown it for j equal to 1, 2, and 3. Can I show it for any j? Can I show it? Can I understand what the probability is? So it's a nice problem to think about. Okay, let me just sort of, make this into a double screen so you can see the two things and think about it. Very nice.